My name's Brandon Bradley, and today I'm going to talk to you about the halting problem, and you, meaning how it applies to you. So, the problem. Stephen Klein said there's no algorithm for deciding whether any given machine, when started from any given initial situation, eventually stops. So, what does that mean? That just means that we can't find an algorithm to detect whether a program will halt or stop. So by scanning the program, not executing it, the program code. So it's a decision problem. It's a yes or no answer to a question. It just so happens to be unsolvable with real machines and abstract computing machines. Real machines such as your laser drone, and abstract computing machines, for example, VirtualBox. You can write code to run on an abstract machine, but you can't do it with this problem. So here's a proof of why you can't solve this problem or write a program to solve this problem. So we're going to assume that we can do that. And let's call it the oracle. The input is any program code, which we're going to call P. And the output is whether it halts or not, the yes or no answer to that question. So here's a simple block diagram. We're going to input a program and output our yes or no answer. So here are some trivial examples. Let's check out just an infinite loop. I think we can all say that it definitely continues forever. It does not halt. And let's talk about another example, the simple instruction of doing nothing. Of course it halts. And sure, that was some good examples, but it has to work for every program that it takes in, not just a few examples. So let's make another program. We're programmers, right? That's what we do. Let's call it the Deceiver. And here's what the Deceiver looks like. In this form, it's a function, but you could write a program that just does this too. It takes the input P, and if the oracle function, which we assumed to be true earlier, or not true, but assume that it exists earlier. And we are going to check and see whether the output of the oracle, the function that detects halting or not, is true. And if it is true, we're going to go into an infinite loop and do nothing forever. If the oracle isn't true, then we're just going to return true to our output of our Deceiver function, and that is the Deceiver function. So here's a block diagram of the Deceiver function. It takes input P, oracle answers yes or no, and the Deceiver either goes into an infinite loop or it outputs true. So here's where the proof gets creative. We're going to refer the Deceiver to himself. At this point you might be getting a little confused, that's okay. But there are two cases that the Deceiver can go into. Either the Deceiver itself loops or it halts. So let's check out both cases. The first case is that the Deceiver loops. Now keep in mind that P right now is basically a copy of the Deceiver itself, the program code, not the running, executing program. So if the Deceiver loops, which is this case, then, if the Deceiver loops, and it's the input to the program itself, the oracle is going to say, no, it doesn't halt, and the Deceiver is going to return true and halt. If the Deceiver halts, then the oracle is going to output, yes, it does halt, and going into an infinite loop. And the deceiver doesn't loop. I'm sorry, I didn't say that right. The deceiver goes into an infinite loop. So what did I just say? What? What? What about what? Well, what the deceiver does is it provides the contradiction. So there's something wrong here, because we can't do this. We don't write programs that make contradictions. So what's wrong here? Oh, by the way, this is written in Python for all you wonderful Python people here. So the function definition looks okay. If statement, I don't know. The third line, the while true, those look all like logical programming, valid programming statements to me. So do the next two lines. So what's wrong here? That's wrong. That's the one thing in this function definition that is not just a regular programming language statement, other than Deceiver, but we have the code of the Deceiver right here, but we don't have the code of the Oracle. So our initial assumption is wrong. So, and what that was that the Oracle exists. So the Oracle can't be written. And that's the end of the proof. So how does that apply to you? Well, I think it's good that there are problems that exist that can't be solved, but have really well-defined definitions. And it just so happens that many of these problems reduce to the halting problem, meaning that you can, in essence, convert them into the halting problem and decide that they don't exist. So it just turns out that the halting problem is one of the canonical unsolvable problems. And it is used to prove a lot of problems are not solvable. And the thing is that we might have this intuition about this kind of thing, but it's simply not enough. We need a formal way to communicate this to other programmers, mathematicians, or whatever your flavor of awesome is. And algorithms are fun, and everybody needs to like them. Well, maybe not needs to like them, but they can be a lot of fun. And I do think that everybody necessarily needs to, let's see, how should I say this? Well, I don't know, but algorithms are fun. So there are some other undecidable problems that are relevant to you, maybe. For example, do two compilers or interpreters accept the same languages? For example, PyPy or CPython, do they accept the same language? Well, guess what? You can't answer that question. Also, the dead code problem. Given a line of code somewhere in your program, does that program ever actually reach that line of code? I don't know, and you probably don't either because you can't solve it.